So hi everyone, thank you for joining this talk today. My name is Tom Benson and I'm currently a research fellow at the MIT Sensible City Lab. I'm actually from the UK originally and I've relocated to the US nearly 2 years ago, and I come from a background of architecture. Having worked in Beijing, Basel and London, but more recently I've been interested in the realm of urban science by combining different methods from fields such as computer science, data analytics, social science, and also, of course, planning. I'm actually still quite fresh to the topics that I will discuss today, but I'm very honoured to actually be part of this conference. I think the organisation by Karen and her team has been absolutely phenomenal, and the rest of the organisers as well has really been really phenomenal during the times that we are currently living in. But also Karen and her team's work was actually really sparked for me when I was reading about urban inequalities. So it was also, a great honour to be part of this conference with her. And also Michael Batty is actually one of my key inspirations. I believe he's actually from the north of England, and if anyone knows anything about British accents will know that that's also where I'm from, so it's nice to see his journey throughout his career. And he also shared an interesting quote in 2015 which I think is relatable, which is about defining big data. Because big data is what you cannot put into an Excel spreadsheet. And he's completely right, because now we need new ways to store it and new ways to analyse it. And the lab I work for at MIT really builds upon this and works on a range of projects, but also seeks to use new methods to understand cities. But today I'm going to share with you the work that we have been doing with the city of Stockholm, and the presentation is called Using Deep Learning to Predict Neighbourhood Change in Stockholm. So this work is actually, as I mentioned, I'm actually part of a lab called the MIT Sensible City Lab, but last year we started an interesting partnership with the city of Stockholm and a university there called KTH, and we began this new lab called MIT KTH Sensible Stockholm Lab. And this lab is really a partnership between these three arms, and it's a direct collaboration. And I think it's also quite interesting and relatable because a lot of the urban displacement work I see is also collaborating very much with people who are able to make policy change and urban decision makers. But it's a partnership that has really been driven by improving the city of Stockholm, and actually through the lens of improving the urban inequalities in the cities. We actually have a few different arms to the different projects, but this one is more focused on the long-term changes of neighbourhoods. And as Karen stated, displacement happens before gentrification takes place. So our motivation here was to see if we can measure neighbourhood changes in real time and in effect create an early warning system for the city to find these vulnerable neighbourhoods. And then this in turn will allow better protection of residents under the threat of being displaced by gentrifiers. And our results can also provide a tool for Stockholm officials to implement policies geared towards the needs of community residents. And like I said, Karen's work was obviously one of the motivating factors in this research, but other key papers are that of Anne Owens and her methodology of measuring ascent neighbourhoods. Minla Ball offered a unique perspective on Stockholm and gentrification, and how 10-year conversion was a key indicator for Stockholm. Edward Glazer started to tease out the concept of using digital data with Yelp in cities in the US, and papers by Jonathan Reeds and Joshua Lee and team provided interesting statistical methods in generating baseline measures of gentrification, along with using machine learning techniques as well. Another paper by Lei Dong, one of my colleagues at the Sensible City Lab, he used Yelp data to predict social economic attributes using restaurant data on 257 cities in China. But for the paper that we are doing here, we believe our contribution to the academic community comes with using data that is being updated in real time from a digital platform, and we also incorporate a time series factor using deep neural networks. Another factor, of course, is that we are able to add Stockholm to our growing list of case studies, as the cities hasn't been deeply studied thus far. So our research question here is, can we use real-time data to predict gentrification in Stockholm for 2025? And the 2025 will make more sense as we move through. But the goal of the project is to find vulnerable neighbourhoods today, but by predicting where future gentrification and exclusion might take place. I don't think our goal is to really have this perfect prediction of how gentrification will be in 5-10 years, as cities are more dynamic than this, but rather having a model in place to offer better protection to residents under the threat of displacement today. And we aim to do this by creating baseline measures of neighbourhoods and categorise them into different typologies, and then use deep learning to predict neighbourhoods of gentrification. Our methodology begins with using principal component analysis to create a single score of neighbourhoods between 2013 and 2019. And for this part, we actually are exploring other techniques which include time series clustering to be able to capture the change of these neighbourhoods, but for now we are sticking with the PCA approach. Then we use the k-means algorithm to then cluster them and categorise neighbourhoods into different neighbourhood typologies. And then with these labels, we are then able to train on time series real estate data from a digital platform in Stockholm and then make these future predictions. Currently we're using LSTM supervised neural network to create this single step classification. And the dataset of real estate leads itself to maybe being a quite obvious one to use in gentrification studies. The data is web scraped from this local platform, and we're able to scrape 6 features such as sale price, size and bedroom. We are maybe looking to expand out of just using real estate data and maybe looking to incorporating Yelp and TripAdvisor reviews, but these platforms aren't really that highly used in Stockholm. But we're also thinking about Google Street View as a component as well. And this platform called Hemnet, the digital platform with real estate data, is still actually in its infancy. So the data we have only really starts from 2013, but the amount of data points since has been growing significantly. So this is why our research is limited to the timeframes of 2013 and 19 to train on, and then 2019 to 2025 to predict to. So the labels that we've created from the PCA and clustering algorithms, and then we conduct a feature engineering on the real estate data to generate over 30 features for our neural network. For the 3 variables that we use for the PCA analysis, first we use the median income value of the neighbourhood, second we measure the number of residents with a college degree, and finally a number of residents with them or their parents that have a foreign background that isn't Swedish. The spatial aggregation of neighbourhoods that is over a population of 100 leaves us with 384 neighbourhoods to measure. We also conduct the PSA on both timeframes 2013 and 19 at the same time to avoid the results being skewed. And just by taking the PSA 1, we can then generate the composite index, which will then give us the socio-economic status score of each neighbourhood. I mean, in these variation graphs, we can see similar results with the income and education levels, which aligns with the literature of these being very similar metrics, which are down here actually. With this score, we're then able to measure the sum difference between 2013 and 19 and map these changes, and starting to reveal which neighbourhoods have started to change the most during this time frame. We also can then score in terms of rank between 1 and 384, and seeing where the rankings have maybe also changed during this time period as well. With these 2 scores, we are then able to label neighbourhoods into ascending, declining or stable. So a neighbourhood that is in the top 20% of the PCA score, or in the top 20% of the Z score generated from the rank change, we can then label this as ascending. If the bottom 20% of PCA change and rank change, we can label this as declining, and then the rest would be labelled as stable. And taking into just the ascending category, taking this into account, we then conduct a clustering method by analysing the different typologies of neighbourhoods, and we use a different data now, which is the starting income, percentage of rent, and we also have a few different variables that are trying to capture this tenure change throughout cities, which has been mentioned in a couple of papers as a key indicator for gentrification in Stockholm. And then we have these 4 categories of just the ascending neighbourhoods: upbringing, marginal gentrification, standard gentrification and super gentrification. And for these graphs here, it's important to note that the data has just been normalized, so just for the ascending category. So for example, if you see a high unemployment, it doesn't really mean in the general context that it's in large decreases in unemployment. But for the upbringing category, we can see in the top bounds of unemployment, and we can actually see higher rates of unemployment and lower rates of percentage of renting, and also a lower case of household income change throughout this years. But we also see an increase in younger population. For marginal gentrification, we see a lower starting income, but in context, a large increase in household income and a growth in young and old population. While we also see the overall owner rate stay similar, the larger increase in tenants over 65 and between 25 was significant, while the population also between 0 and 17 saw a decrease. The population of young professionals between 25 and 29 also increased. For standard gentrification, we see a somewhat similar traits in the former, but we have a large increase in percentage of residents renting and also a sharp decrease in unemployment rate throughout these neighbourhoods. We also see younger generation purchasing a property, but also a decrease in the older population buying. To categorise super gentrification and exclusion due to its large starting income in 2013 and its large increase in household income and percentage of renting throughout time as well. We also see a large increase in older population and a significant decrease in unemployment rates. So with these labels, then we're able to find the neighbourhoods of these four categories, and then we can use these as gentrification labels to train our model and start to understand spatially how gentrification is also taking place throughout the city of Stockholm. But now we have these labels, the data that we actually use to train our model on is from the digital platform called Hemnet, which is a local platform for Sweden that holds real estate information. It actually required a lot of Google Translate, so I'm actually quite nearly fluent in Sweden these days. But the platform is actually updated daily on various information about each sale. And by creating a web scraper, we can actually extract 7 features: sale date, initial listing price, final sale price, year built, number of bedrooms, size of apartment, and the address. And then we can use Google geocoding API to convert the address to a geolocated point. And as I've previously mentioned, this platform is still pretty new, but since 2013 it's had 126,000 sales in the database up to today. And the coverage from 2013 and 19 is also similar, that we can actually use as our bounds in our measurements. As we only have a small number of features, we conduct feature engineering to find age of purchase, normalizing population against price sale, the relationship between price and size of room, measuring the interest between initial price and final sale price, just as some examples of our features. But we're significantly hoping to expand this also with different data sets such as Google Street View as well. As an example, this is actually just showing, this matrix is showing one neighbourhood and the 30 different features that we have, and in this time series format of 7 steps. And what we're trying to capture here is actually these trajectories and patterns throughout with the different labels as well. The model that we are going to create is going to use these multivariants and conduct a single step classification prediction. At the minute we just have 7 steps to our time series model, but we can also build a model with longer steps by incorporating month by month analysis, as the Hemnet data gives us the exact date of the sale, which would nearly give us 100 steps. Currently we are using LSTM model to forecast using the sliding window approach. This method uses prior time steps as training and frames a challenge now similar to a supervised learning approach. We train 2 models on 2 different levels. The first, whether a neighbourhood is gentrified or not, so we have non-gentrification against gentrification, and this is basically a merge of all the different typologies of gentrification that we have in the clustering. And then in this we have 384 neighbourhoods that we can train our data on. The second prediction is now just predicting gentrification typologies as a single, and these are measuring standard gentrification, marginal gentrification, and super gentrification, and this contains 89 neighbourhoods that we are able to train on. Model 1 is simply looking at gentrification, non-gentrification, and the prediction so far has scored pretty well, but there are a few more steps that we can go to improve these scores, more feature engineering, taking into account adjacent neighbourhoods to avoid overfitting in our model is also one key element that we are looking to explore, and also increase the time steps in our model as well. The spillover effect, I think, has been discussed throughout some literature gentrification studies, and I think that's also a big element in actually some of our feature engineering aspects. Model 2 is looking to show the potential with some first initial findings by predicting these three levels of marginal gentrification, standard gentrification and super gentrification, and this model is only looking at the gentrifying neighbourhoods, and again it's starting to show potential of these results. But we also plan in our methodology to test is against actually other measures of gentrification as well as a validation for our results, because there's obviously a number of gentrification methodologies that have been developed, and this has actually been deeply discussed in a paper by Benjamin Priss, which is looking at mapping gentrification and displacement pressure and exploration of 4 distinct methodologies, who's a colleague of mine at the Department of Urban Studies at MIT, and he compares 4 gentrification models in 4 different cities in the US, which is Seattle, LA, Portland and Philadelphia, and he applies all these 4 different methodologies to one city, that of Boston, and he sees varying change in his results. So what I'm trying to do with this methodology is actually seeing if the ones that are in 2019, which you can see here, are they at risk in 2019, or are they actually what I also predicted to change in 2025 in my model as well, combining these 2 efforts. And in effect, this work, we are starting to understand the potential of using data generated by digital platforms like that of Hemnet to create a deep neural network time series classification forecast. And hopefully such a tool of an early warning system can build upon Karen and her team's work and the use of this tool to give better protection to residents in Stockholm. Deep neural networks are still new, I think, to neighbourhood change research, but I think there's clearly a potential here to look at the trajectories of these changes. There's certainly some limitations with this work. I think, the time frame certainly being one of them, being limited by the platform Hemnet, but I think we can begin to overcome this by adding actually more data between our 2 time ranges, but I think also capturing these changes over 10-15 years will certainly add much more to this research. Stockholm also doesn't have an open data platform at the detailed level such as London, so data collection is also quite challenging itself. The data is not readily available, and some data sets that would maybe improve the study are not available for research. But currently also another limitation is, I think, our spatial aggregation. We have 400 neighbourhoods, while some other gentrification studies nearly are deeply into the thousands. So this future work is actually more what I'm planning to do with this work, but it's actually bits I've already sort of mentioned throughout, testing different methodologies on generating the social economic status score and looking into the use of time series clustering to generate ascending, declining and the stable labels. There are also other data sets that we could potentially use in our studies to understand these changes further and find more narratives with our work. Our lab has done significant work with Google Street View, and we believe that this could also add some visual characteristics information to it as well. We also considered using Yelp, but as I mentioned, it's not really that highly used in Sweden. And we're going to continue to get feedback from our collaborators in Sweden to refine our results and methodology. But thank you very much for the opportunity to share this work, and thank you again to Karen and the organisers for putting this together during such times. I look forward to carrying on the conversation. As I'm not able to exchange business cards with you, I've left my virtual business card here. If anyone wants to reach out and talk, I would certainly encourage so we can talk some more. Thank you.